Now, if you look at finite dimensional vector spaces, every finite dimensional vector space in which you can define an inner product is a Hilbert space. There is no problem for completeness in finite dimensional vector spaces. But there will be a problem if you go to infinite dimensional vector space. The problem is the convergence is important only in the infinite dimensional vector space. So two spaces which we construct are, one space is called L square. This is L square of R. And I write like this. This is square integrable space of square integrable function. What does it mean? This is a vector space. This is a Hilbert space. L square of R is a Hilbert space. This is an infinite dimensional Hilbert space. Okay? So let me say that I have a function phi and some function psi in L square of R. When I write like this, that means the domain is R. That means phi is a function of real parameter. But phi itself can be a complex function. Okay, phi, psi are L square of R. Square integrability means okay, so let me write phi is equal to, let's say phi in this, square integrability means that integral minus infinity to infinity or instant integral over the volume integral P3R, because I talked about the real. It can be in general, put it as one dimension because I talked about the R here. So dx from minus infinity to infinity modulus phi of x, the square has to be less than, that means it can never be infinity. Square integrable means the integral of the square of the element is finite. Okay, if it is infinite, then we say it is not integrable. But square integrable means this is the condition. So all set of functions which have this property are called set of square integrable functions. All examples in quantum mechanics are of this type. Okay, take a hydrogen atom, harmonic oscillator, particle in a box, any problem which you have solved, which you have not solved, doesn't matter. All of them are square integrable spaces. This is the Hilbert space that we study in quantum mechanics.
So, here, by definition, it is complete.
Yeah. So, how do you visualize that it is complete? How do you visualize that it is complete? Because see, you construct any sequence of functions in this, any sequence of functions with the property that phi 1 square plus phi 2 square etc. is equal to. So let's say you construct a Cauchy sequence. So let psi 1, psi 2, psi 3 be a Cauchy sequence. Now I have to say what is the sense in which so psi n minus psi m, this one has to go to 0 as n and m goes to infinity. But this is a kind of, these are two functions. So I have to visualize the psi n and psi l, this magnitude, as the norm induced by the inner product. The inner product is given by this kind of a form. Correct? Now by definition, this one has some particular value, this one has some particular value, because these are square integrable functions. Correct? These are square integrable functions. And as you know, since they become closer and closer, their limit point will also be another square integrable function. So by construction, this has completeness property. That is, if you ask what is this norm, this norm is nothing but integral minus infinity to infinity modulus of psi n minus psi m, psi n star minus psi n star into psi n minus psi m dx. Correct? This is the modulus, or square root of this modulus. So here you have psi m star psi n, psi m star psi m, and then psi m star psi n dx and psi n star psi n dx. So you can so if they are, if this sequence of functions, if you can choose them to be so the argument is
It has to be orthogonal also.
they need not be orthogonal. Okay, assuming that in some sense I have written this, that means how to do it is a different question, but Cauchy sequence, you must define some norm which will be 0 between these two. There is a distance which is decreasing between, a well-defined distance decreasing between these two. And then you ask a question, what happens to psi n to the limit n tending to infinity? So it is something like this. In some functional spaces, you have these functions which are whose distance is decreasing, and then it will be having a limit point here. Now, the question is whether this limit point is outside the space or inside the space. Now, this limit point, you can show that since this distance is decreasing, it's almost, the distance decreases here, and you can show, I do not know how easy to show that, but you can show that this one, this limit point is also square integrable. Which means you can write down the limit point. Okay, let me put it this way. So let's say that there is a limit point called n tending to infinity. I will call this particular function called phi. There is a limiting function called phi. Now I can choose a basis. So choose a basis, use a complete orthogonal basis, and then write this phi as sum over n Cn times this basis. So this basis, let me call it as phi n. So Cn times phi n. So this is the limiting point. Okay. Now you can see that if I ask what happens to integral minus infinity to infinity dx of mod phi of x whole square. What happens to dx of mod phi whole square? This is equal to sum over n. Okay, so let me put it this way, integral minus infinity to infinity sum over n Cn star into phi n into sum over n prime Cn prime star phi n prime phi n star. Okay, so this is phi and this is phi star. Okay, let me write this as integral minus infinity to infinity dx. So now this you can write it as I use in summation sum over n comma n prime Cn star Cn prime into integral minus infinity to infinity phi n star into phi n prime dx. But you know, I have talked about orthonormality. Orthonormality means this will be delta n prime. So I can write this as this is an orthonormal basis. So this is delta n prime. Okay, this is delta n prime. So that's equal to only when n prime is equal to n, this n prime summation will be valid. So this is equal to sum over n modulus of Cn square. Okay, so modulus of Cn square, see this d chi of x whole square is equal to modulus of n Cn square. Now, modulus of n Cn square for all n has to be equal to 1, or it has to be at least less than infinity, correct? Because you take any other suppose you take any other function, that is psi n, that is psi n is one of the members in the sequence of that. For this psi n, in the same basis, I can get an equality like this, correct? I can get an equality like this, but there it is equal to, it should be less than infinity because psi n is a square integral function. So I go on getting this one. That means essentially what I am trying to say is, for in this sequence, if you take this term, this term, and this term has got a the square integral equals to, for this term, sum over n mod Cn square has to be less than infinity. Okay. Now the next term is also this kind of a condition as well. And now there is a distance between these two that is going on decreasing. And you have a term here. Let's say for this one, I have sum over n. I will call this as mod dn square. That is also less than infinity. But there is a requirement these two have to go to 0, and then n goes to 0. That means if this is a finite number, this is a finite number, and the difference between these two numbers has to go to 0 is a sufficient quantity, is sufficient to show that the last term also will satisfy this kind of condition, which means the limit point will also be square integral. So this shows that this is square. If this is less than infinity, then it is square. Usually, more rigorous proofs for completeness are possible, but they are generally beyond the scope of any mathematical physics. But if you look at some books by Courant and Hilbert or Jeffries, some pure maths books, there are certain more rigorous mathematical proofs of completeness available.
So the Hilbert space that we encounter in quantum mechanics belongs to only this category.
If you have, see, there are three types of Hilbert spaces we come across in quantum mechanics. One is by this type, where you have any classical relevance. That means You have a classical counterpart. That means you are talking about position, momentum. So from position and momentum, when you are quantizing, you have a quantum mechanical problem involving position, momentum, etc., then all the Hilbert spaces are of this type. But you also do quantum mechanics without having any relevance to position. For example, spin dynamics, angular momentum dynamics. They are all finite dimensional Hilbert spaces. That means you don't have infinite dimension there. There are only finite dimensional Hilbert spaces. But there are also these are the two kinds of things that you have. Only square integrable functions are finite dimensional Hilbert spaces. Only these two types. Either it is square integrable or it is finite dimensional spaces. Angular momentum, spin, all elementary particles, you have Hilbert spaces which are finite dimensional. But if you want to talk about their position, momentum, then you have square integrable Hilbert spaces. So this
separation continuously decreases means can we say that sequence is a converging sequence?
yes, every Cauchy sequences will converge to a limit point. Now the question is whether limit points are inside or outside. Complete space should have all limit points.